Okay, this is going to be our third video in our linear momentum series. And in the last video, we talked about elastic collisions. In this video, we're going to be talking primarily about inelastic collisions. Okay, so we can get started here. An inelastic collision is a collision in which our kinetic energy is not conserved. So our kinetic energy is going to change during this collision. So what might happen? Well, we might have a collision where some of our kinetic energy is lost to other forms. So we could lose some of it to heat, to sound, to deformation of the two objects that are colliding. So this kinetic energy might be dissipated, or we might have some potential energy that's liberated and transformed into kinetic energy. So these two objects could collide, and there could be some sort of chemical energy stored, some sort of explosion happens, giving the system more kinetic energy, or as we're going to look at, we could have a coiled up spring that is released, and the potential energy stored in that spring now becomes kinetic energy in the system. But in any case, what's happening here is basically we have a collision where we have conservation of momentum, but we no longer have conservation of kinetic energy. Okay, so we can't use conservation of kinetic energy to solve these types of problems. So one special case of an inelastic collision is the perfectly inelastic collision. So what's happening in the perfectly inelastic collision is we have two objects which collide, and they stick together during the collision. So they get sort of stuck together during the collision, and after the collision they move off together with the same final velocity, right? So if we remember our notation from last time, our v1 prime indicates the final velocity of object 1 after the collision, and v2 prime is the velocity of object 2 after the collision. But because these two objects stick together during the collision and travel off together, those are both the same, and so we label both of those v prime. Okay, so v1 prime is equal to v2 prime, and we just call that v prime. And this makes it a lot easier for us to solve some problems in some cases, because it eliminates one of our unknown variables, right? Usually we would have an unknown v1 prime and an unknown v2 prime, but now we know that v1 prime is equal to v2 prime, so we only have that one unknown variable. Okay, so I have a couple of examples for us to look at, but before we get into the actual numeric examples, I thought we'd look at a sort of very simple example of what a perfectly inelastic collision might look like, and just take a look at how that might work. So let's imagine a sort of, maybe I'll give this a label, simple, perfectly inelastic collision. Okay. And so initially, let's take a look at two blocks moving in one dimension towards each other, both with equal mass, so mass m. Our first block here has a velocity pointing in this direction, and our second block is going to have the same magnitude of velocity but pointing in the opposite direction, right? So we can imagine this is our positive direction here. So what's happening initially? Let's take a look at the momentum and the kinetic energy initially. So initially, we're going to have some momentum for block 1 plus some momentum for block 2. But we know that that's just m1. Well, I guess I don't need v1 here, but it's going to be mv. And our second block is going to have m and minus v, right? So if we add that up, we're going to see that it gives us a 0, and that's because we have no net initial momentum, right? So the first block has some momentum, and the second block has some momentum, but the net momentum cancels out, and we end up with no net momentum in the system. And what do we have as far as kinetic energy goes? Our kinetic energy initial is going to look like 1/2 mv squared plus 1/2 m minus v squared. But since we're squaring them, the minus sign doesn't really matter, and we just end up with mv squared. Okay, and so we do have some initial kinetic energy. What happens after the two of these collide perfectly inelastically? So our final state here. Well, both of these are going to smash into each other, and because it's a perfectly inelastic collision, they're going to stick to each other. So they're stuck to each other, and normally these things would move off with the same velocity, and they will, but in this case that velocity just happens to be 0, right? Because the two of them slam into each other, and there's no leftover momentum in either direction, right? So they just slam into each other, stick to each other, and they don't move anywhere. So clearly, our final momentum 1 is going to be equal to, well, 0. This thing is not moving, and our final momentum 2 is going to be equal to 0. So our final overall momentum is going to be equal to 0. There was no momentum to begin with, no net momentum, I should say, and there's no net momentum in the final state either. We're also going to see that we've lost all of our kinetic energy. There's no more motion. These two things are just sitting there stuck together. So we can do the same sort of analysis we did in the initial case, but with no velocity. There's going to be no kinetic energy in our first object or in our second object, and so our kinetic energy final is also equal to 0. Okay, and so that was just the sort of simplest case for a perfectly inelastic collision. So let's now move on to another example where we have some numbers in one of these perfectly inelastic collisions. I'm just going to take a quick second to export this because I've been having some issues with this program crashing, and I don't want to lose all this. So let's save this. And let's now take a look at what happens in this example. Okay, so what do we have happening here? We have an object with a mass of 0.15 kilograms moving at a velocity of 35 meters per second. It collides perfectly inelastically in one dimension with an object, and this should be M2, with an object weighing 70, or with a mass of 70 kilograms, which is initially at rest. Okay, and so we want to find in part A what the final velocity of the two objects are, and in part B we want to calculate the amount of kinetic energy lost in the collision. Okay, so let's start off by drawing the problem here. So initially, we have M1. So M1 is much smaller than M2, and it's moving with some V1. That's going to slam into our much larger mass M2. Okay, and M2, I guess I can write it's V2, but we know this is equal to 0. And so what do we expect to happen in our final picture? Well, we know this is a perfectly inelastic collision, so the two of these are going to stick together after the collision. So we'll have M2 here, and M1 will be stuck to it afterward. And since our only momentum originally was a little bit of momentum to the right here, we're expecting that this thing is going to move off to the right with some velocity, probably a much smaller velocity than the initial one because our M2 started off stationary, right? So let's now examine sort of what happens in this setup. So part A, let's see here. Part A, we are trying to solve for the velocity of the final objects. We know that since we're dealing with a perfectly inelastic collision, V1 prime is going to be equal to V2 prime is going to be equal to V prime. And so let's take a look at what our well, we know that we can use conservation of momentum, but we know that we cannot use conservation of energy because this is an inelastic collision, right? So let's take a look at what conservation of momentum gives us. As usual, we can write this down as P1 plus P2 is equal to P1 prime plus P2 prime. And we can write this in terms of the masses and velocities of these objects as follows: M1 V1 plus M2 V2 equals M1 V1 prime plus M2 V2 prime. But we can right away cancel this term because we know that M2 had a V2 of 0, right? It had an initial velocity of 0, so that term is going to go to 0. and we can make use of this condition up here, our perfectly inelastic collision where our final velocities have to be equal to simplify the equation. And if we do that, we end up with m1 v1 is equal to v prime m1 plus m2. Okay, so we're just, basically I've just rewritten the v1 prime and the v2 prime as v prime because we know they're equal, right? And then collected terms up. And so at this point, we really just want to isolate v prime. We're ready to solve if we had the numbers, and we do. So if I isolate v prime, I'm going to find that I have m1 over m1 plus m2, and we still have a v1 on this side. Okay, and we can just substitute in numbers. That's going to be 0.15 over 0.15 plus 70 times 35. Right, and if we do that calculation, we're going to find that v prime is equal to 0.07 meters per second. And that would be our answer for part A. Does it make sense? Let's take a look at our drawing up here. So we started off with v1, well, m1 moving with v1 at 35 meters per second, so it's moving quite quickly, but it's very, very not massive object, right? It's 0.15 kilograms, and it slams into this much larger 70 kilogram object. It sticks to it, and then we're saying that they move off with a velocity of 0.07 meters per second. So that makes sense. They move off with a much smaller velocity, and that's what we found, so that's good. In part B, what are we looking for in part B? We want to calculate the amount of kinetic energy lost in the collision. Okay, so I have those numbers here. Let's start off by just looking at the change in kinetic energy, and that's going to lead us to our lost kinetic energy. So we know that we can write the change in kinetic energy as the initial kinetic energy and the final kinetic energy. So it'll be the final kinetic energy minus kinetic energy initial. What is our initial kinetic energy? Well, that's going to be equal to 1/2 m1 v1 squared plus 1/2 m2 v2 squared. But again, v2 is 0, and so this term will be 0. And what is our final kinetic energy? Well, that's going to be 1/2 m1 v1 prime squared plus 1/2 m2 v2 prime squared, right? But again, our v1 prime and v2 prime are the same, and so I can rewrite this a little bit more cleanly in this form, right? And so now we can substitute in our final kinetic energy and our initial kinetic energy into our change in kinetic energy formula, which we've just written down here, and we're going to end up with the change in kinetic energy is equal to our final kinetic energy, minus our initial kinetic energy. And at this point, again, we're ready to substitute in numbers, right? So we end up with 1/2 0.15 plus 70 times 0.07. We just found that v prime in the previous part, minus 1/2 0.15 35 squared. And if we run the numbers on this, we're going to find that our change in kinetic energy is equal to minus 91.7 joules. So we lose 91.7 joules of kinetic energy in this collision. Okay. Let me again save this so we don't lose this. Save it on my desktop. I guess change that. Okay, good. So let's continue here. I have a third example that we can do, and in this example, or have I lost it? Oh, I have the numbers here. Okay, so in this example, we're going to be taking a look at two carts that are colliding inelastically on an air track. Oh, let me pause this for 1 sec. I'll be right back. Okay, we have so we have two carts traveling inelastically, well, colliding inelastically on an air track. So they're so for I guess it depends when you guys are seeing this, but you may or may not have worked with air tracks in the lab before. But an air track is just this sort of frictionless track that allows objects to collide in one dimension, right? So we can imagine that this is our air track here. And initially we're going to have, I'll just draw these carts on here. So initially we're going to have some cart of mass 1 traveling with some v1 in this direction, and we'll have some other cart of mass 2 traveling with v2 in this direction. Okay? And so these two carts are going to collide inelastically, but there's a little twist here. Cart 1 has this coiled up spring on it. Okay? And in the collision, that spring is going to be released, and all the potential energy stored in the spring is going to be converted into kinetic energy in the system, and we're going to want to solve some problems given the information that we have here. Okay, and so I'm going to draw what the sort of final state also looks like. So we can imagine this is our positive x-axis or something, and these two things are speeding towards each other. They collide. The spring releases its potential energy as kinetic energy, and after the collision, we have the setup I'm drawing here. So we're going to have again M1 on this side. The spring will now be uncoiled. It will have released all of its energy. We're told what M1 prime is, what V1 prime is, and we know that V1 prime is going to be pointing in this direction. And we have M2, but we don't know what V2 prime is, right? V2 prime could point in either direction, so I'm just going to put it in with both directions here. We don't really know what's going to happen to M2, and that's kind of the question. We want to solve what the final velocity of the second cart is. Okay, given that we know mass 1 and mass 2, and we know V1 prime, and V2. Okay, so let's maybe start looking at that solution. So in part A, we are solving for V2 prime, and what do we want to do here? Well, we have an inelastic collision here, so we know that we can still apply conservation of momentum, but conservation of energy is lost to us because we have kinetic energy changing in the system here. So what does conservation of momentum give us? Well, it tells us that P1 plus P2 is equal to P1 prime plus P2 prime. Okay. And we can rewrite this again in terms of the masses and velocities involved here. Excuse me. And if we do that, we will end up with M1 V1 plus M2 V2 equals M1 V1 prime plus M2 V2 prime. Oops. Prime, right. But we're already in a position where we can basically solve this. The only unknown here is V2 prime, right? We know V1, V2, V1 prime. We know both masses. So let's just rearrange this to solve for V2 prime. So we're going to have V2 prime is equal to, well, everything that was on the left-hand side, M1 V1 plus M2 V2. We'll move that other term over, M1 V1 prime, and then divide through by M2. If we do that, we can then substitute in numbers, and we're going to find the following setup here. Minus 0.35 times minus 4 over 0.5. And if we plug this into a calculator, we're going to find that V2 prime is actually equal to 3.7 meters per second. So that's our answer for part A. And let's take a look at what that means in our diagram. So these objects will collide, and V2 prime equal 3.7 meters per second means that our V2 is actually pointing in this direction. And so the mass 2 heads off to the right, okay? And so that's good. Let's take a look at how much potential energy was stored in the spring, given that all of the potential energy was converted to kinetic energy, okay? And so in part B, we're looking at the potential energy stored in the spring. So our change in kinetic energy, if all of the potential energy stored in the spring was converted to kinetic energy, then all of our change in kinetic energy, we will assume, happened because of that release of potential energy. So really what we're looking for is our change in kinetic energy. We know that we can write our change in kinetic energy as kinetic energy final minus kinetic energy initial. What are our final and initial kinetic energies? Well, we know that our kinetic energy final is simply going to be 1/2 m1 v1, that should be a prime, squared, plus 1/2 m2 v2 prime squared. And our initial kinetic energy is going to be 1/2 m1 v1 squared plus 1/2 m2 v2 squared. Okay? And so we can substitute this directly into our change in kinetic energy formula, and we find the following expression. We're going to have our final kinetic energy, so 1/2 m1 v1 prime squared plus 1/2 m2 v2 prime squared minus 1/2 m1 v1 squared minus 1/2 m2 v2 squared. Okay? And we can clean this up a fair bit, so let's do that. We can pull out that factor of 1/2. I'll pull out all the terms that have an m1 in them, so let's do it like this. We'll do m1 v1 prime squared minus v1 squared plus m2 v2 prime squared minus v2 squared. Okay. And again, we're ready to solve here. We can, and I might need more space. So we can substitute in numbers, and if we do that, we're going to find that we have, well, I'll write it out here. So m1 is 0.35. We'll have minus 4 squared minus 2 squared plus 0.5 times 3.7 squared minus 0.5 squared. And if we plug all that into a calculator, well, I guess we can clean it up term by term. We'll end up with a 4.2 over here plus a 6.72 over here. And in the final step, we're going to find that we have a change in kinetic energy equal to 5.46 joules. Okay, so if we assume that that all the kinetic energy that we gained here came from the potential energy, and all the potential energy stored in that spring was in fact turned into kinetic energy, then this is the amount of potential energy that was stored in that spring initially. Okay, so that would be the answer to part B of this. And yeah, so this was our sort of first look at inelastic collisions, perfectly inelastic and just inelastic collisions with a few different twists thrown in there. In the next video, we're going to expand all this stuff to looking at 2 dimensions. So the calculation is going to get a little messier, but we'll leave that for the next video.